Okay, so hello everyone.
Yeah. Welcome back, everyone. So for today's pre-seminar, we have our very own Myriam Mahaman from the University of Berlin, who will be giving a short introduction to Hopf algebroids. Take it away.
Okay. So today I will talk about Hopf algebroids, and they are usually introduced as a generalization of Hopf algebras, where we work over non-commutative base ring. But this afterwards, when people see the definition, they are confused as to why it is so much more complicated than the definition of Hopf algebras. So today I will use a categorical framework of Hopf monads to somehow give an insight as to where the complexity comes from. Okay, so we work with monoidal category C, and a Hopf monad is an endofunctor on that category which satisfies certain properties. And our goal, so on the one hand, we have the classical setting where we work with modules over a commutative ring, and we have the algebroid setting where we work over the bimodules over a ring R, actually an algebra R, which is not necessarily commutative. And in the classical setting, the functor is defined simply by tensoring with an object in the category, whereas in the algebroid setting, we take an RE bimodule and tensor over RE. And here we can already see the difference, whereas in the first one, we use the monoidal structure of the category, and in the other one, we use an external operation to define the functor. And as we will see later, we will express the definition of a Hopf monad in terms of an algebraic structure of the objects we use to define our functors. Okay. So first, a monad is an endofunctor together with two natural transformations. The first one, eta, from the identity to F is called the unit, and mu from F squared to F is called the multiplication. And we expect then mu to be associative and unital with respect to the unit. So being a monad is about the behavior of the functor with respect to composition. And in our setting, so in the classical setting, we recover the notion of a K-algebra. And in the algebroid setting, we obtain an RE ring. So nothing new here. So the subtlety arises when we consider comonoidal functors. So being comonoidal is about the behavior of the functor with respect to the monoidal structure of the category. So a comonoidal functor consists of an endofunctor, a natural transformation, which we can think of as the comultiplication, and one morphism, which we can think of as the counit. And we expect these natural transformation and morphism to be coassociative and counital. In the classical setting, we recover the notion of a K coalgebra. But in the algebroid setting, we need to introduce a new definition. Okay. So we need to define what is called the Takeuchi product. So I will give a more precise definition later, but here I define it in terms of a universal property. That for our RE bimodule A, curly H, there exists an object in the category of RE bimodule such that Okay. We have a bijective correspondence between the natural transformation from tensoring, then applying H to applying H separately and then tensoring. Okay, so we have natural a bijective correspondence between such natural transformations between these two functors and the morphisms of RE bimodules from H to the Takeuchi product. And okay, so that's a nice property. So this property was proven by Day and Street, and it gives us some insight as to why we would choose this operation. And for the counit, so this morphism here would be the counit, and this corresponds to an anchor map from H into the K-linear endomorphism of R. And the Takeuchi product can actually be defined for any pairs of RE bimodules, and it induces a lax monoidal structure on this category, whose unit is NR. And then once we add the coassociativity and counitality, then we obtain the notion of a left coalgebra with respect to the Takeuchi product. And now we are ready to talk about bimonads. So bimonads are endofunctor who are equipped with a monad structure and a comonoidal structure such that both structures are compatible with each other. So in the classical setting, we recovered the notion of a bialgebra, and in the algebroid setting, we obtain a bialgebroid, so a left bialgebroid, because we tensor from the left. Oof. And for okay, so for a bimonad, we still need to define when it is considered Hopf. So whenever we have a bimonad, we have the following natural transformation, which is called the Galois map. So the right Galois map, where here I use the comonoidal structure, and next I use the monad structure. So this composition yields the Galois map, and we say that our bimonad is the right Hopf monad if this natural transformation is invertible. So in the classical setting, we recover the notion of a Hopf algebra. And in the algebroid setting, we obtain what is called a right Hopf algebroid. So notice here, for the tensor product, I use these small symbols, and these, because we have 4 actions of R. So RE, and I use these triangles to refer to them. So here we have 2 white actions, and here we have 2 black actions. And when I write it like this, I mean that I use so on the left, I use the right black action, and on the, wait a moment, this. Okay. And on the right, I use the white action. Okay.
So maybe this is like basically for the
So it's a bit more subtle, because even if this even if the in the algebroid setting, even if the Galois map is invertible, it does not necessarily yield an antipode. And in the classical setting, we recover and we obtain an antipode because the monoidal category is symmetric.
I think of the inverse of alpha n as like you provide a program and then the antipode to only one of the factors. So that's if then you can apply epsilon just to get like the antipode.
Yeah.
So it's more like the inverse of the alpha corresponding.
Okay. So with this we are done with the definition of a Hopf algebroid, and I will recall all the structures once more. So in practice, a Hopf algebroid is some K algebra H together with an RE ring structure. Okay. Oops, what happened? Yes. I have an RE ring structure, which is given by the unit, or equivalently by two maps, which are respectively called the source and target map. And next, we have the cross-R coalgebra structure, which is given by a commultiplication, which goes from H into the Takeuchi product. And concretely, the Takeuchi product is obtained as a subspace, the subspace of this tensor product of H with itself, for which the black actions agree. Okay. And then the compatibility is given by checking. So first, the Takeuchi product, as we defined, is closed under the multiplication. And therefore, we can check the compatibility between the two structures by checking that delta and epsilon hat are ring morphisms. And finally, we check that alpha, that the right Galois map is invertible. And once we have this invertibility, we can define what is called the translation map, which is obtained by applying the inverse of the Galois map on H tensor 1. And the Galois map is defined in such a way that we can recover alpha minus 1 from the translation map. Okay. And let me give some examples of Hopf algebroids. Okay. So here are some examples which are some objects which are often mentioned in this seminar. So first we have the enveloping algebra RE, and it corresponds to the identity functor, and it is a Hopf monad in an obvious way. So next we have groupoids. So groupoids correspond to commutative Hopf algebroids, and they were defined by Ravenel. Okay. Then we have Lie-Reinhardt algebras. Then their universal enveloping algebras are Hopf algebroids. And in this case, the source and target map agree with each other. And finally, an easy way to construct a Hopf algebroid is by gluing a Hopf algebra with an R module algebra upon which it acts. Okay, so I just gave the idea for this example, but let's go. So we will next look into more detail into the Ehresmann-Schauenburg right Hopf algebroid. So first I will recall what is a Hopf-Galois extension. So we start with a Hopf algebra H and a right H comodular algebra A. Okay. And we consider its subalgebra of coinvariance B. Okay. We say that the extension B in A is Hopf-Galois if the canonical map chi here is invertible. So chi is like an analog of the Galois map, but for H comodular algebras. And we assume, okay, and once we have this invertible map, then just like for the Galois map of Hopf algebroids, we can also define a translation map. So here it goes from H to A tensor BA. Okay. And okay, we need to make one additional assumption. So we need to assume that A is faithfully flat over B in order to get the nice property for these objects. Okay. So here are the structures we have. Now let us define our Hopf algebroid. Okay. So I take A tensor A. It has a natural right commodule structure over H, and then take the coinvariance inside that commodule. Then we can check that if I consider H as a subspace of A tensor A up, then it is closed under multiplication and it contains the unit. Therefore, H has a natural K-algebra structure. Okay. It also has a natural BE ring structure, which is given by just sending the elements of B to each side of the tensor product. Okay. And now we will use the translation map in order to define the commodification of our algebroid to be. Okay. So we take, okay, I forgot to mention. So here, the elements are not necessarily simple tensor as written like this. So they are sums, but for simplicity, I just write simple tensors. So I take my tensor product, I do the coaction, and then apply the translation map to the middle element. And as a result, I obtain an element in H tensor BH. And the co-unit is simply obtained by co-multiplication. And from there, using the properties, so we use all the properties of the Hopf-Galois extension to show that delta is indeed well defined. It is multiplicative, so it lands in the Takeuchi product and it is multiplicative. And and therefore we obtain a left bialgebroid over B. And we would like to have a right Hopf algebroid structure on it. So without doing anything, we have a left Hopf algebroid. But because we won't write one, we have the following results, which from what I understood was shown by Thomas and Niels Kowalczyk, that if the antipode of the Hopf algebra is involutive, then we do have a right Hopf algebroid structure whose translation map is obtained as follows. Okay, so here I use this pointy Sweetler notation to denote the translation map of, then it should be A prime. Like this. Okay. Okay, so, and with this, we have defined what is called the Ehresmann-Schauenburg right Hopf algebroid. So, yes. Good. Okay. Hopefully there are no more typos. Okay. Okay. And so earlier, so in the previous definition, I used the right. So I use the right H comodule, but if we start with a left H comodule instead, then we obtain again a right Hopf algebroid.
Yeah, so really just very
Mhm.
briefly comment. So this is really our fault. It's not Myriam's fault that this complication appears. It's just if you want to have a left by algebroid, right Hopf algebroid, you should have started with a left H commodule algebra. We started first with right, then understood okay, it's not going the right way. So now you either assume S square equal 1, or if you don't want this, you look at everything left, then without any assumption, you can make this work. Yeah, thanks for keeping up with the next.
Okay, so with this, I am done with the example, and I will not talk about comodules over. So comodules over a Hopf algebroid. Okay. So when we have a monad, then we can also define the notion of a module of a monad, which consists of an object in the category we work over, together with a morphism from Fm to M, which is compatible with the monad structure of F. And so with the functors we are interested in, we recover the usual notion of a module over a ring. And now we have, so we consider bimonads, and the bimonad structure translates into an additional structure on the category of modules. Okay. So there is a bijective correspondence between the bimonad structures on F and the monoidal structures on the category of modules, which is obtained from lifting the monoidal structure on C. Okay. And what else? Yes. And given a bimonad, being Hopf also has such a categorical interpretation that the bimonad F is right Hopf if and only if. Okay, first we need to assume that the base category is right closed. So this means that the tensoring from the left admits right adjoint. I do not understand why such a terminology for the left versus right. Okay, so if we assume that C is right closed, then we have that the bimonad F is a right Hopf monad if and only if the closed structure on C lifts to the category of modules over F. And for the last topic, I will talk about comodules. So the notion of a comodule over a comonoidal functor is a bit complicated. So it was defined by Aguiar and Chase as some functors. So there exists the notion of a module category, which is a category M upon which the monoidal category C acts upon. A comodule, a left comodule over the functor F is then a functor on that category M, together with a natural transformation, which is compatible with the comonoidal structure on F. So that's all I will say about the categorical definition of comodules. And in the classical setting, we recover the usual definition of a comodule. And in the algebroid setting, we define comodules using the Takeuchi product, which is expected. Okay. And now once again, I will explain how a bimonad structure on the comonoidal structure will result in an additional structure on the category of all comodules. Okay. So if our comonoidal functor is a bimonad, then the category of comodules is monoidal, where the monoidal structure is just the composition of functors. Okay, what do I want to say? Okay. So I forgot. Yes. So, and similarly, we can also define the notion of right comodules. Okay, whereas this time we use an action of the monoidal category on the right. Okay, and we still have the same result as we had previously. And I think, yes.
From monoidal, right? So,
strict monoidal means that we have an equality, not just an isomorphism.
So it's even case more than from, okay.
Yes. Okay. So, okay, and with this we are done, and I will summarize one last time the structures that we have on associated to our left bialgebroid. So if we have a left bialgebroid structure on H is equivalent to a monoidal structure on its category of left modules, where the monoidal structure is just the one of R bimodules. So this is the tensor product and this is the unit. Furthermore, if it is a left bialgebroid, then its category of so we have a monoidal structure on its category of left and right comodules. And finally, being right Hopf is equivalent to the category of left H modules being right closed, where the inner Hom for that closed structure is just given by the R linear maps between the underlying structure of bimodules. And before we finish, I want to make a small remark about the left versus right modules of our Hopf algebroid. Okay, so we had that if H is an RE ring, then if tensoring from the left, or if we start with an RE bimodule, then tensoring from the left is a monad if and only if tensoring from the right is also a monad. So here we have an additional structure that does not exist if we only work purely with functors. However, we have that this functor being comonoidal does not imply that the tensoring from the right is comonoidal. And that's why we have that in general for a Hopf algebroid, the category of, okay, so for a left bialgebroid, the category of left modules is always monoidal, but the category of right H modules is not monoidal. Okay, and this is an important point for Thomas's work because they need to consider right actions of a algebroid in order to define the notion of a Hopf module over them. And with this, I conclude my talk. Thank you for your attention.
Questions for Myriam?
This was very interesting. And does it make sense to talk about quasi-triangularity for category of models over an algebroid?
Yes, it does. So quasi-triangularity corresponds to having a braiding on its category of left H modules, and I do not know how exactly it translates into a structure on H, but it makes sense.
And it is the usual braid group that we all know for Hopf
Yes.
algebra. Okay. Okay, thank you.
Okay, so I don't know if I can express well myself, but when you define the Hopf algebroid or the property for the end of functor such that you get an Hopf algebroid, you said that classically for the category of K modules, you get that you recover a proper antipode because the category is symmetric. But so you cannot make sense of this definition of Hopf algebroid in the braided setting. I mean, because of this, like what I want to ask maybe is this construction, what does it recover if in the second line I consider another category, like Dieter-Drinfeld modules, for example, this property of the Galois map being invertible?
I think in general, it will recover the notion of a Hopf-monoid if we assume that the category C is braided monoidal.
Okay, thank you.
A very basic question. This Takeuchi product, to make sense of this thing, okay, there were the fancy universal properties, but like the concrete definition looked a bit like a cotensor product to me. Is that
Like cotensor product.
I mean, you know, you can bring the thing across.
Yes, it's defined as a center inside of a tensor product. And so this the fact that taking this center is necessary in order to make the things swap around when we apply the tensor product. Can it be thought of as a
Like a mixture of an ordinary tensor product and then a cotensor product on the outside somehow. But if you like consider it as the cotensor product over the joule. So if you've got a cotensor product with co-modules, then you take the joule guy, you can have, it looks like this where you can bring it across.
I remember I saw some presentation of this Takeuchi tensor product where they were using some target and source map that in some way were like a right coaction and left coaction, and you want these to coincide. So I guess you can.
Because yeah, there's the one that is, sorry.
So one way to think of it is that so if we have Um, so if I have H, so via the anchor map, we can think of the elements of H as functions in N R. And okay, let me erase. So if I have functions in N R, and I would like to make a functions from out of them. I want to make functions from a tensor R into R. The way to do so is just to take F tensor G, and then I map it to, I apply F and G, and then I multiply. Yes. On the other hand, I have the one way to go from the k-linear endomorphism up here, where if I just have some F, then I apply to the product. And in theory, if we had a co-multiplication, then it would go from here to here. And if I look at all the actions, then if I, so the image of the elements here are the maps such that if I multiply first A by some element X, and B, then this is the same as F1 A and X B. So this is always true. Therefore, some elements up here which should satisfy this property should it's called H. H. When I write it down, then I should require that H of AX G of B should be equal to H of A times G of X B. Okay. So this is the idea behind it, and this is how it looks like when we write it formally using the actions.
Any questions from the online audience? If not, then let us thank Myriam again. We'll take a quick 5-minute break for the main seminar by Thomas.